So yeah, thanks for the opportunity to speak. Today I'm going to talk about some ongoing work in my group where we found a method that can extract hard-to-measure information theoretic quantities from quantum simulator experiments. This work is done in collaboration with these people, and I believe both Akash and Ayush are in the audience, so if you have further questions, feel free to find me or find them after the talk. Good, so let me put, I said that I'm going to talk about information theoretic quantities, how to measure them, but let me just put it in a more broader context. So we're dealing with, our goal is to do data extrapolation. It's a fancier version, it's called analytic continuation, but basically we try to do data extrapolation. Seems like a simple problem, but it turns out to be highly non-trivial in real settings with finite amount of data and noise in the data. So we will start from this broad context, and then we will talk about a particular case. How do you extract von Neumann entanglement entropy from quantum simulator experiments, where you can measure Laimei Nie entropies? So in particular, the method we're going to use is called stabilized analytic continuation. We combine it with the established randomized measurement toolbox. And then we'll be doing some simple tests on the method just to show that it works, and then apply it to the actual trapped ion quantum simulator data. And finally, if time allows, I'll talk about what else can we do with this method. Okay, so in broader context, data extrapolation. We are asking if we know certain range, data range of a function, can we predict this function's value outside the range? This looks like a simple problem that should have been solved, but it's actually not easy. So in particular, we are dealing with the special case where this underlying function is analytic. Suppose it's analytic on the complex plane. Now, given finite data values, can you predict the function at another point? So why do we care about analytic continuation? Well, as I said, certain information theoretic quantities such as von Neumann entropy comes from analytic continuation from easier to obtain quantities like Laimei Nie. So I will talk about how exactly people can measure Laimei Nie these days in quantum simulator. Another application of analytic continuation is in quantum Monte Carlo simulation. So in Monte Carlo simulation, you get Green's function at Matsubara imaginary frequencies. But what you want to really get is Green's function at real frequency so that you can compare with the spectral function measured in experiments. So how to go from Matsubara frequency to real frequency, that's a long-standing problem in quantum Monte Carlo simulation. So it requires analytic continuation, a good method of analytic continuation as well. Okay, so some theoretical abstract questions. First thing you can ask is analytic continuation unique? The answer is sort of. In the ideal case, it is unique. So what I mean by that is that if I have two analytic functions, if they satisfy certain conditions, then you can show that they are the same function. There is uniqueness. So they need to be both not growing too fast in the complex plane, at the infinity of the complex plane. And then if they also both take the same values at all the non-negative integer points on the real axis, if they satisfy these two conditions, not growing fast, and also they take the same values here, then they are the same function. That's a theorem in complex analysis called Carson's theorem. So that theorem guarantees that in this ideal case, where you know infinite data points exactly, you know that there's only one function that suits all the criteria. So if you do analytic continuation, you get one answer. That's good. But in reality, we don't have this perfect data set. We only have finite amount of data, and those data have noise. So how can you do analytic continuation? How do you do data extrapolation with this imperfect data set? So the question is how to do that. And the answer is, well, we found a method called stabilized analytic continuation. So a caveat of this method is that you do need some additional constraint, because without those additional constraints, you're not going to uniquely determine the function. So we will have some reasonable physical additional constraint added to the setup. Okay, so let's just take a case study of just to show you how this stabilized analytic continuation works. The case study is extracting von Neumann entropy. So for this audience, I don't need to say too much about why von Neumann entropy is important. This is by no means a complete list. Many of you have worked in this field. So a lot of theory work has been done regarding von Neumann entropy and its associated quantities, like topological entanglement entropy. The question is, can we measure it experimentally? Well, it is hard. For von Neumann entropy, you have to measure the density matrix because it's log row, so you need to know the full knowledge of the density matrix. And that turns out to be hard. You're limited by system size. So alternatively, you can measure something called Raney entropies that only involves the density matrix moments. And this density matrix moments is easier to measure. Recently, there's some advance in so-called randomized measurement toolbox and shadow tomography, which allow you to measure those in a faster, like more resource-conserved fashion. So the basic idea is you have your quantum system, say quantum simulator, trapped ion system. Question? You mean for randomized measurement? Yeah. So this is still exponentially hard, but it's half of the exponent. So it's better, but not ideal. But it's still, I think full state is like 4 to the n, and this is like 2 to the n, something like that. Yeah. So for experiment, you can go up to 20 qubits, if I remember correctly. Yeah. So the idea of randomized measurement is the following. You have a quantum simulator platform where you have single site control, okay? And you first do a round of random rotation. Those are drawn from hard unitaries. And then you measure along the z direction. So after these steps, you will get a bunch of bit strings, either zeros or ones. And then you just repeat the measurements many times. You get a lot of bit strings. And then you change the unitaries many times. And in total, you would do measurements m times k times. You have these many bit strings. And using those classical bit strings, you can reconstruct quantities like observables or density matrix moments. So in particular, for our case, the density matrix moments can be expressed using the so-called shadow density matrices. Those are reconstructed using the classical bit strings. So this is called classical randomized measurements and classical shadow because you're casting your quantum states to some classical realm. Those are the bit strings, and you use those bit strings to reconstruct partial information of your original state. And the more measurements you do, the better accuracy you have. So in reality, people have obtained Renyi 2 to Renyi 6, or density matrix second power to sixth power in a quantum simulator. So with some noise, but that's the data we have. Okay, so you can say that, well, we can just use von Neumann, Renyi as a proxy of von Neumann, as we have been doing in a lot of cases. But there might be some problems with that because sometimes they can have different behaviors. For instance, for systems with U1 conserved charge, we know that von Neumann grows ballistically with time, but Renyi sometimes can grow diffusively. And a lot of the quantum information theorems are written for von Neumann entropy, not for Renyi entropy. And from the ADS-CFT perspective, this ADS-CFT duality dictionary is better established for von Neumann, but not for Renyis. Okay, so there are many reasons why we should think about experimentally measuring von Neumann instead of just Renyis. So the goal is, how do we get von Neumann from experimental Renyi data? Okay, So this is a data extrapolation problem. So you would think that people have solved it, but actually not really. So people have tried a lot of different methods. So for instance, Taylor series. So you can expand this row log row in Taylor series, and you turn this into basically a sum of density matrix moments sum, and you truncate at some point. But then in reality, what we did test, we found that you have to keep this n very, very high to make the truncation error small, like n a few hundred. That trace row to the 100 is not achievable in current experiments. So you have to, there's like a lot of difficulty associated with Taylor series truncations. Or you can try polynomial fitting, for instance, least square or Chebyshev polynomials. You can also try something called max entropy. This is a standard technique that people in quantum Monte Carlo do. But you realize that all those traditional methods have the following drawbacks. The first is that they are better for interpolation, not for extrapolation. So interpolation is, I want to know this point, but this point is within the data range. But we are doing extrapolation. And it turns out that you can encounter overfitting. Like data here change a little bit. This function can, because say polynomial fitting, can fluctuate wildly outside the data range. And another thing is that they're not robust against noise. So to address those two problems, here is our strategy, the stabilized analytic continuation. I should make it clear that we didn't invent this method. This was invented by Sully and Spearman in 1980s. So it was invented just for the purpose of addressing analytic continuation in physics in general. And we adapted to the Renyi entropy, von Neumann entropy problem. So the key idea of this method is instead of doing brute force data fitting or polynomial fitting, let's use the analytic property of the underlying Renyi function. So I turn this Renyi index into a complex number, and this is a complex function. So next I will describe how this method works. It's maybe a little bit technical. Feel free to interrupt me anytime. Let's define the discrepancy function. Call it D. So this function has two terms. One is my Renyi divided by a pole, z minus 1. Another term still has this pole, but with a variational parameter. Alpha is something we want to tune. So this discrepancy function always has a pole unless at z equals to 1, unless alpha cancels as z at z equals to 1, which is von Neumann entropy. So the idea is I can tune alpha, and if it hits the von Neumann entropy, the pole structure disappears. So our goal is to see when the pole structure disappears by tuning alpha. Okay, so let me just make it more pictorial. So this is the z-plane. I have a pole at z equals to 1 for this function. And you can show that this function is analytic on the right-hand side of z equals to 1. So there's some caveat here. I'm happy to talk about it offline, but let's assume it is analytic in this half plane. And we also know this function's value at some integer points, say from z equals to 2 to z equals to 7. The goal is to find the best alpha such that this function's pole disappears. Okay, to do that, let me first do some technical maneuver. Let's map the half plane into a unit disk. This is just for the sake of our convenience. Map things from infinity to finite, so easier to deal with. This is done by a conformal mapping so that the pole at z equals to 1 maps to w equals to minus 1, and infinity in z maps to w equals to plus 1. Those integer points, 2, 3, 4, blah, 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 they map to the points on the real axis within the unit disk. Okay, how do we know if the pole structure is suppressed? First of all, if we know the function's value at infinite points, and we also know the function is analytic within the unit disk, then we know the function exactly. That's Carson's theorem. So we can say we will tune alpha and see when the pole is suppressed. But that's not what we have. We only have access to a finite set of data points. So to determine what the function looks like, we will need additional constraints. So the additional constraint is imposed on the boundary. So this is our choice. Maybe there are some other good constraint you can add, but we choose it to be on the boundary. So in particular, this is the constraint. So let's define a norm that looks like this. So it's basically this function's imaginary part derivative of angle theta when the function is on the unit circle. So the detailed form of this norm doesn't really matter at this stage. What you need to know are two things about this norm. One is this integrand. As your function diverges near the pole, this integrand also diverges near the pole as you approach the pole on the unit circle. So there's some divergence going on here. This integrand contributes the most when it's near the pole. Another aspect of this norm is the I will mention soon. So they're basically minimization problems. So two-step minimization. I want to first minimize this norm over all analytic functions in my function space that take on the required value here. So I want my analytic function to take required value here, but also has the minimal norm on the circle. Minimal norm because, as I said, this integrand this norm has the most contribution from the pole. And if you want to see when the pole structure is suppressed, you're equivalently looking for the norm is minimized. And this minimization problem can be mapped to a maximization problem using a functional analysis theorem called duality theorem. So Sully and Spearman worked out the details. So this is the technical crux of this method. So you don't actually do the minimization, but you map it to a maximization. And that allows you to find the best function in your functional space. And this mapping is possible because we chose this norm. If you chose some other weird norms, that still diverges, but that doesn't fit the duality theorem. So that's another reason why we have to use this norm. Okay, so we find the best function that does the minimization or does the maximization. This function still carries this label alpha, our variational parameter. So the next step is to minimize this best functions norm over alpha. And that gives you the best alpha, which is our von Neumann prediction. So this is how this method works in general. I should also say that here we're only treating data points with no noise. And the next question is how to do this method when the data points have noise. Okay, so to incorporate noise in the data, it's actually quite easy. Basically, we include the so-called chi-square goodness of fit criterion. So this is when you do data fitting with when the data has noise, this is what you do. D0 is the original data points. D is your guessed function's value at that point. So there's some difference. And you weight that difference by how much error you have in the original data points. The larger the error, the less weight it carries. And you want your goodness of fit to be smaller than some chosen value, that you choose it based on your desired level of precision. For us, things are more complicated than this simple formula because we have correlated noise. The Renyis, their noise are correlated. They're not independent Gaussian noise. And to take care of correlated noise, you change the chi-square into from diagonal only to containing off-diagonal terms. So this C matrix here is the covariance matrix. I might have, this should be C inverse, but it's the covariance matrix that describes the correlation of data points of, say, range 2 to range 6. If you have range 2 to range 6, your covariance matrix will be 5 by 5 matrix. Describe how the ranges are correlated. So you can use this as your way to deal with noise, and practically, it basically adds a Lagrange multiplier to the minimization problem. It doesn't change things too much. So noise is actually not hard to take care of in our method. Okay, so that's all theory. Let's now test this method in some simple model. The first test, very simple test. Let's just look at the ground state of transverse field Ising model away from critical point. So, and I look at the half-chain von Neumann entropy of that state. So this is no noise added to the Rényi entropies. And I'm plotting the error percentage of my estimation, so how far away my estimation is from the true von Neumann entropy, as a function of number of Rényi entropies used. So I can use just 2 Rényis or up to 8, 9, 10 Rényis. And different colors are different methods, and you see that, okay, say least square still performs pretty well compared to our method, stabilized analytic continuation. The error percentage is pretty small, like less than 1%. But once you turn on noise, I can add, say, 10% uncorrelated Gaussian noise to each of my Rényi data and see how different methods perform. You see that the stabilized analytic continuation is the most stable one, but other methods starts to deviate, starts to have very large error rate. And this is 10% Gaussian noise added, and you see that the error percentage of my SAC method is also around 10%. So our method is not amplifying the noise you already have. So that's probably the best you can do. Okay, so that's a very naive test because it's naive because we don't have correlated noise. We're just adding white noise to the Rényis and see how methods perform. Let's do a more sophisticated test, which is actually simulating what the trapped ion experiment. So the trapped ion experiment, we're simulating not on the trapped ion, but on a classical computer. So this is the Hamiltonian. It's a long-range spin 1/2 Hamiltonian with fields and with decoherence. So you take into account everything. You try to mimic the experiment, and then you simulate it by quenching a new state using this Hamiltonian and see how the Rényis and von Neumann evolve with time. So there are 2 things you can do. One is you can exactly simulate the system by solving the master's equation. That gives you the true von Neumann entropy. You can also pretend that you're dealing with quantum simulator. You do randomized measurements on the system on a classical computer. And you get the Rényi entropies with noise, and you do our method, SAC, and you get the von Neumann estimate. So this is like doing the actual randomized measurement experiments, but on a classical computer, and you can compare how our method does with a true value. So this is the result. We are looking at a 5-site subsystem out of a 10-site system. And then this is 5 milliseconds after the quench. This is Rényi entropy and von Neumann entropy as a function of the Rényi index. So these are the Rényi data from doing randomized measurements on this classical computer. And the black star is the true von Neumann entropy by solving the master's equation exactly. And different methods here, the SAC does, again, the best. It's closest to the true von Neumann entropy. And other methods could, like this one, fails pretty badly. Yeah. And you can also plot, this is the von Neumann entropy as a function of the time after the quench. So we were looking at 5 milliseconds, which is these data, but you can plot other time step as well. And you see that the SAC is always the best method compared to other methods. It is underestimating the true von Neumann, the black star, partially because the Rényi entropies we feed into the SAC come from randomized measurement. And those Raney entropies from randomized measurements actually are smaller than the true Raney entropy if you solve the system exactly, like numerically, honestly run the system. So your Raneys are already smaller. So that's why it gives a smaller von Neumann entropy as well. But overall, it's the best performing method. And so in this plot, you may say that, okay, maybe other methods are not that far off. But in other cases we tested, there could be incidences where the other methods just give you wild answers. So it's unpredictable. Our methods consistently produce the best result. Yeah.
Because if I understand correctly, the method doesn't know anything about entities, right? It just knows that there is a sequence that needs to converge.
Exactly. Yes. It doesn't know it's an entropy. It doesn't have to be entropy underlying function, but you need to know it's analytic. That's very important. Yeah. Yeah. So finally, we can apply it to the actual experimental data. So this is a 10 trapped ion system. We're looking at the half chain entropy, and the Raney entropies of this has been measured by those people, and this is the time after the quench. So the same setup as simulation, but right now on a quantum simulator. So darker color is Raney 6, lightest color is Raney 2. And now you can give me the data, and I can just feed it into our method and give you the prediction of the von Neumann. So this is the result. We have nothing to compare to, unfortunately, because it's the actual experiment, but this is our prediction. Yeah. So finally, in the 1 minute or negative 1 minute, I can just briefly mention what else can we do with the method. So immediate generalization is, can we extract other information theoretic quantities, like logarithmic negativity? And theoretically, it should be doable, but technically, it may be hard because this logarithmic negativity comes from like even number of Raneys, and so you only have half of your data. You can't use the odd Raney, so that might be a problem. You can also try to extract past Raney mutual information. But beyond, say, other information theoretic quantities, another thing that we're trying to do is extract topological entanglement entropy from, say, DMRG data. So in DMRG, you can measure, in cylinder construction, you can measure Raney entropy easier than von Neumann entropy, but it's harder to extract topological entanglement entropy from Raney entropy for some reason. So the ideal case is if you can first do analytic continuation from Raney to von Neumann and then extract topological entanglement entropy from von Neumann, that would be great. So this is in collaboration with Dr. Hongchen Jiang from SLAC. Finally, we would love to try it on quantum Monte Carlo data. So interestingly, recently Emmanuel Gall and his group has a series of papers of similar ideas of using the analytic property of the underlying Green's function and to do analytic continuation in Monte Carlo. They call it a Navan-Lina analytic continuation. It's based on some 18th century math work. It's quite interesting. So it will be nice to compare if we can apply our method to QMC and compare our result with theirs. So yeah, that's the end of my talk.
Does it have to be something nonlinear in the density matrix? Because in quantum computing, everybody's doing the error mitigation. Very simple, right? You just have observables at various error rates, and everybody's, I think, kind of struggling with extrapolating those to zero error. You know what I mean? The zero noise extrapolation. Like people just assume, oh, it's a linear fit or it's an exponential fit, but I think it's all kind of ad hoc. And I wonder whether this seems a bit less biased. Maybe you put less assumptions, so maybe you can. But I'm not sure if you can actually do it because here you're applying this to this. Do you need the shadows for that, and do you need this to be like a nonlinear in the density matrix kind of thing? No.
No, I don't think you need the nonlinearity. You need the analytic property of the function.
Yeah, I think that's fine.
So you need some modeling of the noise.
Yeah, but like you put a quantum circuits, you put channels in, and that's some high order polynomial in the noise. I think it's over for any finite circuit. I think that's fine.
Then it should be possible. If you know it's analytic, then it should be possible.
Yeah, I think it has to be. Yeah.
Yeah.
Okay.
Yeah. So this is like a fancy version of data extrapolation, basically this method.
Okay.
Yeah. So I think it should be applicable to that as well. Yeah.
Thanks. Yeah.
Yeah, thanks. I'm not too familiar with these methods, but I think some clarification. So if the number of Raineys you have diverges and also the noise is controlled in some way, can you prove that it converges to the correct value?
Good.
And then the second question is like this optimization you're doing, can you talk about complexity of the difficulty of that optimization?
Oh, I see. So the first question, we actually tried that. We want to see if it recovers Carson's theorem. That's what you're saying.
Well, some like
kind
approximate version of that theorem.
Yeah, but there's in the end, we couldn't do that because there's an infinite sum that we couldn't handle.
But you think it's true, or
we are not sure. We're not sure. I cannot comment to very certainly on that, but that's a good question. We tried it, but for now we didn't succeed. Yeah. And for the second question, so this is a numerical method, and it's hard to, you're asking if I can give an upper bound of the error.
The optimization problem, like will you get stuck in local maxima? Or?
Yeah, so there's a possibility of doing that. We don't have an estimation of the upper, error bound. Yeah, but it's similar to ask what is the error bound for other traditional methods.
Yeah, right. No,
yeah,
yeah. Thanks.
You mentioned that there are examples where the other methods sort of fail and give kind of garbage results. Can you say a little bit on when that happens?
Yeah, so it's actually this trying to extract topological entanglement entropy in toric code and also Heisenberg model on Kagome lattice. I can show you the data afterwards, but it just sometimes in toric code in some parameters regime some methods work, but if you go to Kagome, then it doesn't work. Yeah.
Hi, thank you for a nice talk. So sometimes people care about lower Rayleigh entropies, say Rayleigh 1/2. I was wondering if the presence of the pole at the von Neumann prevents you from continuing to those, or if you can go around somehow the pole within this method.
Sorry, what do you mean by lower Rayleigh?
Rayleigh 1/2, for example.
Oh, yeah. I see. No, I think we can do Rayleigh 1/2. Yeah. It shouldn't be a problem.
Okay, great.
Yeah.
Another small question. You mentioned in passing that the data for the Rayleighs 2, 3, 4, and so on was actually systematically a bit lower than the experimental one. So the data obtained with randomized measurements was systematically lower than what it should have been, I think you mentioned.
This plot? This is lower than?
Maybe. No, I think, yes. Yeah, this one, I think you said that maybe the data from shadows was systematically lower than it was supposed to be.
Oh,
right?
I see.
I thought that, so my question is, I thought that shadows were an unbiased estimator, but am I wrong in thinking that?
Shadow is unbiased estimator,
okay,
yeah.
So do you understand why?
Let's see. There are some error bars, but they're very small here. Let me see.
I think it might have been like.
Yeah, I think it's the vertical axis. This is also very tiny. Yeah, so this is from simulation, and it's this very small order, although it looks big, but because of the axes. This is on a much bigger scale, and there's also tiny error bars. Are you asking why?
So that's I may misunderstood, but I thought you said that it was systematically, like this, it wasn't statistical error, but it was a systematic underestimate. Systematic underestimate. I see. Yeah. Okay, I see what you mean. So here I'm saying this is small than the true value, partially because the rays we feed in is smaller. That's just by observation. It's okay.
Smaller.
So that was my question. Just an observation. You don't have an understanding of why that is?
Yeah, I don't have a good understanding. In theory, if you do infinite number of measurements, the mean should converge to the true value. It is an unbiased estimator. Yeah, but because we only have finite data, so it's off. But I don't understand exactly why it's lower.
The bias of an estimator should be should hold for a finite number of samples, right? So maybe that is not unbiased. Yeah, that's what I'm wondering. Okay. That would be...
Oh, I see. Okay, yeah, I can think more about it. That's a good question. I will double check the basic use statistics literature. Yeah.
Just quickly, so you commented on using this to extrapolate to, to get topological entanglement from numerical data. Can you comment, based on the errors and so on, about, whether it's feasible to measure subleading terms in entanglement using these methods from like actual experimental systems?
Subleading, you mean system size?
Well, like topological entanglement, right? Where I'm not just interested in the entanglement entropy of the two halves, but rather I have to compute some difference. And the question is, like, in practice, with the errors that you can realistically expect from finite sampling on experimental data, are those terms accessible?
So right now, we haven't extracted the topological entanglement entropy yet. We're just looking at the entanglement entropy with, so there's this volume, error law piece and then a gamma piece. So I don't know too much about how the finite size scaling is done in this DMRG experiment, so I shouldn't comment too confident on that. But right now the data looks very clean. Like the data has very little noise, the DMRG data. So I personally would think it should be.
But I meant the experimental data.
Oh, I see.
Which is that's the point. Like in numerics, I believe that you can compute these things to very high accuracy. In an experiment, it's maybe less clear.
Yeah, but in experiments, you want to extract gamma from experiment.
Yes.
But then you have to do finite size scaling.
Yes.
You probably, okay, that might be a little bit challenging. Yeah.
I wanted to ask a question. You had, on the noiseless case, you had an early plot where there was like an error floor for the SAC.
Yes, like this one?
Yeah, I guess, do you have a comment on like why sort of that happens?
Which, you mean this?
Yeah, like near the bottom.
Near the bottom, like why does it drop or something like that?
Or no, why does it plateau? Do you have, like,
plateau.
Yeah.
Oh, this one. Like if you add, is that a plateau?
Or no, just for the noiseless.
Just for the
case.
noiseless case. Let's see. Yeah, so, okay. Yeah, so maybe, let me see. There could be some optimized number of ranges beyond which you don't gain much. That's where you're asking, I guess. Okay, so I think on one side, if you include more ranges, you do have more data points. Maybe that help. You have more information, so maybe that will help lower the error rate. But at the same time, more data points. Okay, I don't have an explanation for noiseless case. I have an explanation for noisy case. Yeah, for noiseless case, it's kind of random. It can go up a little bit. But for noisy case, you see that it kind of plateaus. Well, it also goes up a little bit. But there's some optimized range index where you do gain more information by going beyond. But also, the higher ranges have more noise, typically. Yeah, and then so it's a trade-off. So there's some optimized range index. But yeah, I'm not too sure about the noiseless case. Yeah.
Okay, thanks.
Yeah, perhaps just a follow-up question to that. If I just think of this as like an entropy estimation, like in principle, if I have a finite number of ranges, like they don't contain enough informational content to provide the full and von Neumann entropy. So I might get worried that there's some like fundamental bound. So I guess the question is like, is there any understanding of the analytical continuation method you use? Like, does that bias towards certain type of distribution? Like, or like, is there any sort of heavily tailed distribution that would be weird, maybe not very physical, that where this method would like lead to a large bias?
That's a very good question. So the method has there was a caveat that I swept under the rug, which is assuming the function is analytic in this domain. In reality, it's not. There will be a finite width strip around the real axis where it is analytic. Sometimes the strip is very wide, it's almost an infinity. But sometimes, depending on the spectrum, certain type of spectrum can have a very, very narrow analytic domain. And that might make the method perform worse. So, but those, we're still exploring those kind of spectrum, but they are kind of very rare. Yeah.
Right. Like, do you have any comments on what type of physical system, or are they actually physical that could lead to this weird behavior?
So I think the spectrum that could give you very narrow analytic domain, hence worse performance, is some like dominating eigenvalue. Sorry. Ayush, is Ayush here? Is it the dominating eigenvalue or is the equipartition? So it will be dominating eigenvalue, and then the other eigenvalue very small, and that will be.
I see. So in that case, in principle, there could be other methods for like doing the estimation if it is highly concentrated on one eigenvalue.
Yeah, so that could be a problem. Yeah, but you can tune. There are some parameters like this conformal mapping. This is a simplified version of the conformal mapping, but we do have a better version that takes care of this finite width strip. There are parameters in that conformal mapping. You can tune that to make your performance better. Yeah, but that's case by case. Yeah.
Okay, if there are no other questions, let's thank Laimei again for the nice talk.